What's this thing? It's a cylinder. I happen to have one here. Okay. So we're going to switch from area to volume. How do I find the volume of this thing? Okay, so do you know that answer because you went home and memorized volume formulas? Or do you know that answer because of a concept? Do you understand my question? You memorized the formula.
Yes.
Right? Capital B times H. Capital B times capital H, area of the base times the height. So I'm going to try to get you to change your thinking. Because if I get you to change your thinking about the volume of this, it'll make things a lot easier. So for instance, if we're looking for the volume of this thing, what is this thing, by the way? Hexagonal prism. Very good. Very good. Hexagonal, not pyramid, prism. If we want to find the volume of this hexagonal, I almost said it wrong, prism, how would you do it? Right. Okay, so here's what I'm going to try to get you to do. See how the bottom of this cylinder is blue? I'm going to get you to think about the volume as a stack of quarters. Okay. Now, those quarters, there's some catches here. Those quarters are going to have to be really, really skinny. How skinny? Infinitely skinny. Good. And then how many would I have stacked on top? An infinite. Okay, so we're going to get some conceptual stuff here that geometry kids can't handle. But I'm going to suggest that you look at this, not prism, this is a cylinder. The volume of this cylinder as taking one of the bases and stacking an infinite number of those bases on top of each other. And if I can find the area of this blue bottom, and I can figure out some way to add up all those bases, how would I add up all those bases? Well, I would need some type of accumulator. What could we use? An integral might work nicely. And add up all those bases together, we'll end up with the volume. This guy, same thing. This guy, same thing. Uh-oh. Where you going?
Remember, I have my moving at first.
Oh, yeah, okay, drive safe.
I will try.
Or drive fast and take risks.
That'll probably be one of them.
Cool. What about this guy? Creates a problem, right? For the sake of you watching the video, I'm holding a square pyramid. Why doesn't the concept that we did with this work here? Say again?
It's not the same shape. Or like size.
Yeah, I did bring a box with me, but the bottom's a square. How else does this differ from, let's say, this guy? All these bases are the same here. This time the base is changing. Thank you for the confirmation. We should be able, however, to come up with a way to not care about this and write a general expression for the area of this base regardless of how high up here we chose to work with. Okay. And we're going to do just that. We're going to focus mainly on this thing. So if you can find the volume of this cylinder using that concept, then we'll be fine. And actually, we're going to start by turning it sideways. Okay. I don't know if I can turn this guy sideways. Let's see. Nope, those are... Oh! No. No. That's the dot, sorry. Oh! Oh! Sweet Jesus! Nice. Okay, we're going to turn it sideways. And then, not only are we going to turn it sideways, we're going to put it on a coordinate plane. And find the volume of that. Okay. So, here's another part that's going to cause some confusion. I want to create a cylinder by rotating something. Take a shape and spin it. What shape would I start with?
Rectangle.
Beautiful. If I take a rectangle and I spin it, I'll end up with a cylinder. Now, that won't work for the triangular prism or the hexagonal prism, or not even for that pyramid, no way. Okay. But for the cylinder, it'll work just fine. Are you okay with the concept before we move forward?
Yeah.
Okay, good. Okay, so let's then do this. This is what's called the disk method. Based on the previous discussion we just had, instead of thinking of it as bases, the blue part of that cylinder, we're going to think of them as disks, like a quarter. Not hula hoops. That's something different. So these are called solids of revolution. They're figures that are created by spinning things around and creating a three-dimensional object. Does anybody know what a lathe is? Drew, tell us.
Spin like wood around or like a, yeah.
Yeah.
That's how you like make designs. and
Right,
stuff.
like table legs and stuff.
Yeah.
Yeah, you take a piece of wood, you put it on this machine, it spins it at high velocity, and then you cut stuff out of it, and you end up shading it into usually a circle, but sometimes they have like beads on them and stuff, but it's the way that you design fancy table legs and things like that. That's what we're going to do, which is eventually going to lead us to finding the volume. Eventually we're going to get to something called the washer method, which gets a little bit more complicated, but if you do okay with the disk method, the washer method isn't that bad. And then, if you haven't already done so, at least 2 hugs today. How many are you at?
0.
0? Well, you got 2 to go.
How many are you at?
1 so far. Mr. Schnell. I'm sure he'll appreciate me mentioning that in the video. Okay, so here's what we're going to do. We're going to take the rectangle that we've talked about all along, this representative rectangle, but this time I decided to make that rectangle big and fat like you expect a rectangle to look like. It has a width, which is not dx or dy yet, it's just a width. It's a physical rectangle that you can see. And if I spin that puppy, I get that disk on the bottom there. That disk has a radius, which we're going to need, capital R. We'll switch back and forth between capital R and lowercase r, depending on the shape that we're dealing with. So, everybody good to go with this? All right. Now, this is calculus. So why is this disk not going to work for us? Say again?
I don't know.
Okay. Good. So how do we make it more calculus friendly? Good. And how do I do that?
Spread out the size. Unfold it.
I don't know if I understand what you're saying.
Like,
Like more sheet of paper.
like represent each face.
Oh, lay it out in what's called a net.
Yeah.
But then we go from volume, which is 3D, to area, which is 2D. And we still want to find the volume. Okay. Remember when we talked about the quarters? What did we say about the quarters? Infinitely skinny or infinitely short. Same thing is true here. We want that W to shrink really, really small. Okay. So the volume of that disk is simply just a cylinder. You told me that already. I just changed some of the variables. Pi r squared times W, where W is the height of that cylinder. You want to put a W in there, go ahead. But again, we're working horizontally, so W for me made a little bit more sense. It's the width of that thingamajigger. And like we said, because it's calculus, we want to shrink that width very, very small so that we get a whole bunch of them. Okay, so this is what we're starting with. If I stack those discs on top, if I stack those discs on top of each other, we get a figure like on the right. It's a little hard to see, but you see that red function in there, that f of x? That's what I want to be the shape. Not this stepped thing, looking like a flower pot or whatever that thing is on the side. So we want to shrink the width of those rectangles so that eventually they get really, really skinny, and we get a volume that's very, very accurate. What does that picture remind you of? Trapezoid rule, or those are rectangles. What's that guy's name? Riemann sums. Very good. This is a Riemann sum. And as we said when we do Riemann sums, we either have, well, we have 2 choices. we either make the rectangles real skinny or we make an infinite number of rectangles. This is what we want it to look like, something nice and smooth. Not this big blocky thing on the right. We want the center one, this pretty little shape, which gives us an accurate representation using that thing on the left. Okay, still have a delta x, and eventually that delta x is going to become what? Dx, good. Yeah, we're going to shrink it down so it's infinitely small, which gives us an infinite number of disks. Did I lose anybody yet?
Yeah.
Where did I lose you?
Yes.
I
Are we
just
just
don't
going
know
over
what.
concepts right
Yeah.
now?
Yeah, the mechanics is coming up in a second.
Okay.
And I would argue that as easy as it is to just ignore this stuff, the problems will be easier if you understand the concepts instead of just plugging and chugging. A lot of people just try to memorize this chapter, and I know where we're going and I know the formulas that we're going to use. That causes a lot of problems because it's very easy to get them confused.
Are there like a lot of formulas?
Yeah.
That's fun.
Yeah, it's going to be a blast. I love this stuff. Okay, so we talked about that already. Shrink the thickness, increase the number of disks. Okay, so now I've got this cool demo. I hope this works. I hope this works. I hope this works. Yes, it's going to work. Okay, so we're going to look at the blue thing. And I couldn't fit it all on the screen, so I turned it back up and down. I'm starting with a rectangle. That's our quote-unquote representative rectangle. And I'm going to take that representative rectangle and I'm going to spin it around the axis of revolution. Initially, when you start, your axis of revolution will be the x-axis or the y-axis, depending on which way you're working. But what's going to happen is that puppy is going to spin and make that disk. Okay. Now you see that you have a physical representation of a disk there. It has a radius, it has a thickness, but that's not going to work for us as we progress through the problem, because we want that that thickness to get very small. So we reset this, we get rid of all of that stuff. How do I reset this? I forget. Reset. Okay. Yeah. Okay. If I shrink this point P and move it up, it's not moving right now. All right, let's do this. Wait, this guy. That's the one. Okay, this board doesn't like me. This worked really well on my computer. Never mind, we'll move on. Okay. So now we introduce the same idea. Take a nice easy function, square root of x, and we spin that. I want to take this. So you're going to be calculating the volume of that thing, whatever you want to call that thing. If you can find the volume of that black disk in the middle, or that black disk on the end, or that black disk on the left, you can find the volume of this thing, no problem. It's an easy calculation.
Are you just showing this, or are we going to use this app or whatever? Or are we
No.
gonna just show it?
This is just a demo. This app is really old and outdated, but it does a nice job of showing you what it is you're trying to find.
So if you had like a straight line, it would be like a cone, right?
Correct. Yeah. So how would you get a cone? Well, it'd have to go through the origin
Yeah.
and then go up at some angle. And then when you spin it, because you take a triangle and spin around the axis of revolution, you get that figure.
Wait, so why are we doing this stuff instead of like base times height? So why are we finding infinite stuff that
Good. How does this differ than this?
that's 3D, that's not?
Hold on.
Oh,
Now all of a sudden that's 3D. Or this one, that's 3D too. So Noah asked a good question. What's the difference between that and this?
Well, that one has like a
That's
definite
the
start.
base,
Say again?
It's like enclosed, like it has Oh, you're going to the bases.
Drew.
That has a consistent like base area.
Yeah, notice this radius never changes throughout the whole way. Here,
For the prisoners,
the radius gets smaller as I move to the left.
for the pyramids.
Okay. That's going to create a problem. Because it's not just a base times height calculation anymore, because the base continues every time you move a little bit further to the left or to the right. Okay, so now that forces us to do the calculus, as opposed to geometry where you can just big B times big H, you're done. Okay. So that's one of them, and then you do all of them, and you end up with that puppy. And again, we want to shrink that very small so that it works out the way we want it. No. Okay, so let's actually do it. Graph that. Sketch a graph of x squared plus 3, and the line x equals 2, and the line x equals negative 2, and the x-axis. So I want to make sure that first you can get the region that we're talking about. Remember, it's got to be bounded, meaning it has a finite region, or finite area, I should say. And once you sketch that region, now it becomes the visualization drill, the Zen moment, if you will. What is that thing going to look like when you spin it around the x-axis? Okay, so you want to be able to transition from 2 dimensions to 3 dimensions. It's like doing manufacturing. Anybody ever used a 3D printer?
Yes.
Okay. The 3D printers that we have here at Prospect use this exact method to create 3D printed things. It does a stack upon a stack upon a stack upon a stack. Good. Let's see, I'm gonna go ahead and spin it around the x-axis. Okay, good, it's gonna look like that. Holy smokes.
Is that right?
No, I depends.
That's not what I was thinking. Oh, it's like below it.
So we have a parabola that's moved up 3. We have the vertical lines x equals 2 and x equals negative 2, and the x-axis, which creates our bounded region, which is in yellow. And when we spin that puppy, we end up with that green-looking anti-donut.
So our bounded region
Or
is like.
it's actually what you would get if you were able to cut out the center of a donut after it's been made. It wouldn't actually be a donut hole like a munchkin.
Oh.
That's a lie that Dunkin' Donuts has perpetuated over the years. That's actually what a donut hole would look like. Yeah. Yeah, it is just like a wheel. It's not a good way to start a question. I'll
No,
start over.
I said I'm.
Okay, is this going to become a therapy session now?
That, the green thing.
Yes,
right,
sir.
That's what a donut hole would look like?
Yep.
Oh my goodness. There are a lot of ways about that.
Ah, what? I need like an actual donut hole to see that.
Well, that is an actual donut hole. That's what it would look like.
That's what it looks like.
If you
For
take-
the donut.
Okay, so the technical, we're all on the same page with it. We're talking about a regular donut, not like a Long John or an apple fritter.
Yeah.
We're talking a plain old, like,
If you cook the donut fully,
yes,
no holes taken out.
right.
You took-
To make a traditional donut, the thing you would have to cut out would look like that green thing.
I'm on the same page.
Oh wait, yeah, I get that. I was thinking like a long john, and I was like, what? But yeah.
But Long John doesn't have a hole in it.
I know. I was thinking cutting a hole in the middle of it. I'm like, wait, what the? So
No, are you okay?
brain fart. Okay.
Oh my
Brain
god.
Brain fart.
Okay, so here's the fun now. We're going to find the area, the volume of that thing. And so to find the volume of that thing, we go back to the representative rectangle. And so you're going to start to see why the discussion I had earlier about how important this representative rectangle is going to play a crucial role in this calculation. So it goes like this. I want to find the volume of the disk. So when we did area, we found the area of the rectangle and then accumulated. What we're going to do here is we're going to find the volume of the blue disk and then accumulate all the blue disks to get the green donut hole. So we're going to go baby steps here. Let's start with this. What's the area of that blue rectangle? First question, we're going to use the KISS method here. Am I talking in terms of X or in terms of Y? X, because it's vertical. Good. Next question, what's the area of that thing? Let's do the easy part. How wide is that? Dx, good. So we'll put that over there. How wide is that rectangle? Sorry, how tall is that rectangle? Good, which in this case would be?
Squared plus 3 minus.
0. Good. I'm going to put the minus 0 in there just so that we understand this top minus bottom. Are we okay so far? This is the same thing as the radius
Why is the 0 there?
because it's top minus bottom. Parabola minus x-axis.
Oh, okay.
And you know what? I'm not going to use capital R here. I'm going to use lowercase r. That's the same thing as our radius of our disk. So if we now jump over to this guy, where we've got that disk rotator revolved in there, I want to make sure I use the right terminology. I now want to find the volume of that disk right there on the right. So the volume of that thing, from the previous slides, we know the volume is pi r squared times the width. But we already have the width. The width of that thing is dx. That's easy. Pi times the radius, x squared plus 3, quantity squared. Okay so far? Let's take a deep breath. Any questions? Working in terms of x, find the area of the rectangle. The height of that rectangle is the same thing as the radius of the disk that revolves around the axis.
Why did you put the rectangle there?
You can put it wherever you want. And notice, if I move the rectangle over here,
Yeah.
everything's going to still be the same. Because the top is still the parabola, the bottom is still the x-axis. Okay.
What's the formula? Because the y isn't the one you use.
Yeah, so well, I haven't done the complete volume yet. I'm not finished. This is just the volume of that blue disk. Okay. Now, the total volume of the donut hole, the green thing, is going to be accumulating all of those disks from what to what?
-2 to 2.
Good. How do you solve that integral? Yeah, you got to multiply it out. First thing I would do is slap that pi out in front because it's a constant. It doesn't matter. So this would be pi times the integral from -2 to 2 of x to the 4th plus 6x squared plus 9 dx.
Let's say that it wasn't -0 for the A part, would I put that in for the radius? Okay.
It can get fairly ugly. And so one of the things, go ahead.
I just like for like tests and quizzes, are we gonna be able to like use like our calculators to like do these ones that are kind of like more complex?
The more complex ones, you'll either not have to solve them and just set them up, or it'll be
Okay.
something you can reasonably do.
Okay.
Even though this is ugly, it's doable.
Yeah.
Well, yeah. I mean, the worst case scenario here is you have to find 2 to the 5th.
Yeah.
2, 4, 8, 16, 32. That's workable. I'm not going to ask you to find something like 17 to the 5th without a calculator.
Yeah. Okay.
Okay.
That'd
With it.
be,
Yeah, that'd be harsh. Okay.
we could do it though.
Sure. Okay, so I don't care about the answer right now. That's not what we're talking about. Before I move on, I want to make sure or I want to try to make sure that you understand the concept here. Where did I lose you? Go.
So how do you know that x squared plus 3 is the radius?
Because that's the height of my rectangle. And so the height of that rectangle, if I take that puppy and I spin it, it becomes that disk there. And that's what I want to find the volume of. Okay? Anybody else? Let's suppose, just for fun, that I took this whole thing and shifted it up before I spun it. So it's not sitting on the x-axis. Correct. How to do it is irrelevant right now. What would it look like? A donut hole with a hole in it. Well said. And what shape would the hole in a donut hole be? It'd be a cylinder. We'll get to that later. I just want to make sure. So right now you're gonna start by solving problems where the representative rectangle is touching the axis of revolution. So one thing I do in my pictures is I put a little arrow there so that I can denote what my axis of revolution is. I'm spinning around the x-axis. The types of problems that we do from this point forward become very different. So for instance, I already addressed one possibility, shift that whole thing up and then spin it around the x-axis. What if I spin it around the y-axis? Completely different shape. Can you visualize that?
Yeah.
Only
yeah.
almost becomes like a cup.
Yeah.
Okay. Good.
I did that.
Now the one good thing we have going for us is that we're not going to do anything bizarre like spin it around the line y equals x. We're going to only spin it up and down or left and right. Okay? Anything else before I move on? Yeah, we did all that. Okay, good. Good. I think we'll stop here before your brain runs out of your head. Okay?
It's already been on. Just hold it on.
Okay, we have 5 chances for. They're different problems.
That could be.